Good evening, guys. Can you guys hear me?
Yes, we can hear you.
Yeah.
Yes.
So, before we start today's lecture session, any questions and concerns or issues we need to address?
I have a question about the homework. For the graphs, do you want us to do it like on MATLAB and then just print out the PDF, or how do you want us to do that?
It's fine. I mean, if you want to use Excel sheet and plot it, that's fine. If you want to use MATLAB and plot the figure, that's fine. So whatever is convenient for you is fine. You can also draw sketch using graph paper or by using scale, ruler, or a hand.
All right, thank you.
Okay, no problem.
Professor, the homework is on Beachboard, like the assignment?
Yes, it is in the beach board. The due date is this weekend. I mean, this Friday, I believe, 16th.
Yeah, this Friday.
Oh, okay. Sounds good.
Yeah, for those of you who are not aware of the homework, it is posted in the beach board, and I hope that you have your notifications turned on in the beach board so that whatever is uploaded in the beach board or whatever material is uploaded in the beach board, you should be able to get automated notifications. Otherwise, you will lose track of the important submission assignments or any other deliverables. So please keep track of the materials that are uploaded in the beach board. Okay. Okay, before we start our lecture, any other questions and concerns, guys? So I posted the today's lecture slides as well in the beach board, and one SolidWorks on assembly and two parts as well. We will go through that during this lecture. So they are uploaded in the beach board, so you can download them and you can basically use them for today's lecture for our reference as a reference. So having said that, if there are no other questions, let me actually share my screen. So is it visible to everybody so far?
Yes.
Great. Okay, so today we are going to continue our discussions on the concepts we have been learning so far for the last 2 weeks, which is about stress, or basically how to represent stresses in the material. So today we will be focusing not only the stress components, because by now I believe you have pretty good handle or good understanding, or if not, you already have by now the concepts from 373 and other subject matter that you have covered in the past semesters. So okay, so yeah, the voice keeps on cutting because I use a lot of pauses while constructing my sentences. So it may be that you may feel that the voice is getting cut off, but maybe it is not. It is just like the way that I'm speaking here. Okay,
It's
so
it's the audio going down and up. You can hear it. It's like you start whispering and then it goes back up.
Yeah, I think it's like a noise gate issue or something. It has to do with your mic settings, I think.
okay, I need to address, I mean, after this lecture, I will try to figure out if I can address that issue, but I will try to speak a bit louder so that the audio does not get cut out automatically.
Okay, thank you.
Yeah, is it making, I mean, is it audible to all as of now?
Yeah, it is. It just does it sometimes.
Yeah,
I
it just
see.
happens occasionally.
I see. Okay, so in this lecture, what we are going to do is review some of the concepts that we have been learning so far, and then we will move towards failure theories and how the failure theories can be applied for different types of materials, whether it is ductile materials or whether it is brittle materials. So to begin with, this specific slide basically represents a finite element mesh generated in Abacus software, not in SolidWorks, because SolidWorks does not give such uniform mesh in the geometry. So this is another software, I mean, mesh generated using another software, excuse me. And here you are just seeing one simple component, a rounded hollow cylinder, and it is subjected to compressive load from one end, and it is fixed at the other end. So basically you may consider that this specific component is being subjected to compressive stresses. And what I'm actually showing here or highlighting here is one stress element. Basically means that one find element I am trying to zoom in and trying to see what type of stresses are appearing on that. So if I actually zoom in, and based on the Cartesian coordinates that you are looking at this slide, the stresses that you will actually find in this stress element will be in the y direction. That's what sigma yy is. Sorry, is that their specific chat window? There was some message, so I'm not sure what it is related to. But if you have any question, please, you may ask, and you may interrupt me at any time, at any point of time. So everybody is okay so far?
Yep.
Yes.
Yes.
Yeah, great. So here what we are seeing or looking at is how the stresses will appear on a specific element or stress element, which is a part of this hollow cylinder. And since it is being subjected to compressive load, you are basically only finding the stresses, the normal stresses, which are appearing in the y direction, sigma yy. Going to the next slide, here you are actually having the same component, same hollow cylinder, but instead of the compressive stresses, you are applying twisting moment or torque. So when you apply a movement like that or twisting moment like that, so the whole component or the whole cylinder will basically twist. And when doing that, the stresses that will originate will be on two faces which are adjacent to each other in the direction of the axis. Stresses, the non-zero stresses will be tau xy. X basically in the direction of the x, I mean, in the direction where the stress is acting, and on the plane whose normal is y. So that is why it is tau xy. So you have to be a bit careful about these subscripts, as I have been mentioning you so far in the lectures, past lectures, that these subscripts will play an important role when you are trying to make sense of the results from the SolidWorks simulation or any other simulation software. So when we will see in one case, specific case, that how the stresses are appearing in the material or how they actually get estimated and how they are calculated. And if we are not careful about these subscripts, the results will not make sense to us. So that is the reason that I have been spending a lot of time in making sure that you understand the importance of the subscripts, that what the subscripts basically mean. If somebody asks you to calculate stresses due to twisting moment, everybody knows that twisting moment, stresses due to twisting moment can be calculated using this formula, where the formula for this specific geometrical component is T is a twisting load, torsional moment, R is the radius of this cylindrical object, and J is the polar moment of inertia. So using just simple formula, you can find a magnitude, but at the same time, you have to be careful about what should be the subscript, whether it should be XY, whether it should be XZ, whether it should be YZ. So this has to be you have to be a bit careful going forward while handling or while discussing or calculating the stresses. So similarly, the last loading scenario is bending load. You are applying a load. It's now basically like a cantilever beam. You have load acting at the free end, and the fixed end is geometrically constrained. You cannot move at the fixed end. So if now I have the same geometry of the object, if I have the same stress element I'm looking at, now the stresses will be along the y direction, because my Cartesian coordinate is such that the y direction is along the direction. So that means I have sigma yy basically acting on these two faces. And the reason you have got delta sigma bending and absence of delta sigma bending, can anybody volunteer to explain, or can anybody guess why is it that you have delta sigma bending and no delta at the back face of this element? Can anybody volunteer from the class to explain why is it like that?
Is it due to the change in y as it's being pushed down?
No, it's not. Well, partially yes, it is because of change in y, but it is not the complete answer. Anybody? I mean, it's definitely in the right direction. Anybody can follow on that and follow that track.
Is it because there's a sigma pulling one way and like it's being pulled both ways technically? I don't know how to phrase it.
No, not going in the right direction. I mean, the first speaker who said that about it's because of the y changing. Of course, its y is changing. And okay, let me actually go back to this slide. So here you see there is no such delta tau xy. So the back face and the front face, even if there is y displacement, stress element from the two faces are separated apart, but still you do not see any increment or decrement. There is no delta increment or delta. If I go back one more slide, and this is about the axial stresses, here also you see sigma yy compressive are acting on the back face and the front face, but there is no such increment of the stress being shown. It is just like sigma compressive, and sigma compressive is what is being applied. So coming back, shear stresses, back face and front face, same magnitude, there is no increment and decrement. But the moment I talk about the bending stresses, I am adding this delta. So can anybody try to attempt why it is happening?
Is it because the back face is fixed?
Back face is fixed, but that is a part of the boundary condition. Well, that is fixed in all the other cases. So it is fixed in this case as well. It is fixed in this case as well.
Wait, can you re-explain, Professor, how the previous one relates to this one? Yeah, the moment.
Sorry, come again.
Or can you repeat? Can you re-explain how the torque relates to the other one, or like what you said previously?
The torque does not relate to the third slide. So this torque is basically you are just twisting it. You are just trying to, I mean, just imagine that you are screwing or unscrewing the fastener, or basically you are just twisting the cap of a bottle. So you're applying a twisting moment. So you're just trying to rotate it about its axis, rotate the cross section about its axis. So that is what your twisting moment means here. Do you see what I'm saying?
Oh yeah, it's like if you're holding the end and you're twisting it.
Yes, but when I'm talking about this bending load, I'm not twisting it. I'm just applying a load at the free end, just like a cantilever beam. I'm pulling it in the bottom in the z direction, the bottom z direction, negative z direction. So I'm just pulling it. When I'm pulling it, because of my pulling action, it becomes a cantilever beam, because you know that one end is fixed, another end is having a load. And because of that, the stresses will generate. And this is a bending scenario we have been learning so far. It's cantilever beam. And because of the cantilever beam or the bending load, you have normal stresses primarily, and the normal stresses, which we are representing by sigma bending, which is calculated using this formula. But at the same time, I am using this delta increment, which is missing so far in the other cases. And my question for you guys was, why is this happening, or why is this occurring? Any clue, guys?
Is it because the force, since you have two different points on the cube that you're looking at, the point that's going to be closer to the non-fixed end is going to have a greater moment than the one that's closer to the fixed end. So you need to account for the difference.
Yes, that's the correct answer. So so I don't, let me actually share the document and then show. So if you see this specific scenario where you have a cantilever beam, and this is, let's say, y. Now sigma bending is given by mz by I, right? That's what actually it has to be z, not y in my slides. Okay, so it should be mz divided by I. Is everybody following it so far? What I'm writing it here?
Yes, we are.
Yeah.
So what should be the axis here? It should be z here. So it is z, and x's here. Let me know if this makes sense. The Cartesian coordinate system that I'm drawing makes sense to you. It's a right-hand coordinate system. X-axis is across. This is the cross section of this beam. X-axis, Z-axis, and this is the longitudinal axis. Y direction, Y coordinate is basically pointing this way. Z is pointing this way. Let me know if you guys agree with this.
Yeah.
Yeah.
Yes.
Yeah, everybody is good, fine. Now, what I am saying that bending stresses, sigma bending, that bend, because of this, everybody agrees that this will actually deflect, just like a cantilever beam, where the top part will be in tension, the bottom part will be in compression, and the tension part, the stresses will be calculated by this formula, M times Z, bending moment times the Z. Z is the distance from the neutral axis. So if this is your neutral axis, so distance from the neutral axis divided by the moment of inertia or area moment of inertia. Everybody agrees with me?
Yes.
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 Yeah.
Yeah. Now, if you look at this specific term, bending moment is calculated at a specific distance from the free end by what? So at free end, after a distance y1 from the free end, the bending moment at this cross section would be what? Bending moment at section AA would be P times y1. Everybody agrees with me?
Yes.
Yeah. And if I have a cross section slightly away from AA at a delta y increment, what would be my bending moment? My bending moment would be P, load remains same, but instead of y1, it will be y1 plus delta y. Is everybody agreeing with that?
Yes.
Yes.
Yeah. And because of this, the stress at the front face will be function of only y1, and the stress at the back face would be a function of y1 plus delta y. So because of the delta y increment that is coming, the bending moment actually changes. And because the bending moment changes, so my stresses will also change. Sigma AA would be MAA times Z divided by delta sigma A, it will be MBB divided multiplied by Z divided by I. Is everybody following what I'm trying to say?
Yes.
Yeah. I'm asking everybody if you are following it or you are not. If you are not,
Yeah.
let me know.
Yeah.
If you are with me, then we will move to the next slide.
Can you just give us a sec to copy, Professor? I don't know about anyone else, but it kind of got stuck for like a couple seconds while you were writing that bottom part.
So I believe it is just the Wi-Fi signal. It's causing issues, and it's if I'm basically taking the class from the college, so I'm not sure how to increase that. I mean, how to improve that signal strength and bandwidth.
So that right under where you have stress AA is equal to the moment AA times that Z. What does that Z
Yeah.
represent?
Z represents a distance from the neutral axis.
Oh, okay. No, it seemed like you were multiplying it as a variable. That's why I got kind of confused.
Oh, okay.
Sorry.
That's okay.
MAAT and I.
Is everybody with me? Any questions, guys?
I just have one question.
Yeah.
At the moment for BB, why is it y1 plus delta y, and why is it not minus delta y?
Because you are increasing the distance from the free end. So you are basically calculating the distance from this end, the application of load to this point, which is y1. Now you are improving or you are incrementing delta y. Now delta y can be positive or negative. I don't know whether you are basically delta y is this end. If it is in this end, it will be positive. It will be in this side, it will be negative. So depending on which side you are talking about delta y, it will be positive or negative. Now since my y is positive, y is in this direction going inwards. That's why I asked you guys to make sure that you agree with me on the coordinate system. My y is going this direction, positive y. Z is up, and x is this direction, and z is this direction. If you agree with me on this coordinate systems, then y is positive going this way, and that is why delta y is positive going this way.
Okay, that makes sense. Thank you.
Great. Any other questions, guys? Cool. So let me go back to the slide format. Okay, so everybody agrees now, or everybody understands why I have put delta increment in here. Now I just changed here Z, it has to be Z in the slides that I uploaded in the Beachboard. It's not Z, it's written Y. It should not be Y, it should be Z. So you have to make correction, or I will upload the new slides later on. Okay, so with that said, now that clears some of the concepts that we have been trying to cover so far about the stresses due to independent bending moment, independent twisting moment, and independent axial stress. Now, most of the time, what will happen that in the design of the machine components or any specific components you are going, or engineering component or structural component you are going to work with, the loads will be combination of your bending, twisting, and axial. You will never be have the situation where it is only bending, or it will be only compressive or tensile, or it will be only twisting. So if you have all different combination of loads appearing, then in that scenario, what type of stresses will be appearing in the material and how to take into account of all the different combination of stresses. So that is why you see here, we talk about the Mohr circle. Last time we talked about how the Mohr circle can be used to determine the principal stresses and help us to identify which plane or how the failure will take place in a material. So for ductile materials, we saw that the ductile materials are weak in shear and they basically fail at the value of the maximum shear stress. So if you have a Mohr circle, so imagine for Mohr circle, we always constructed using planar case. So you see that you have for 3-dimensional, you have 3 Mohr circle. 3 Mohr circle corresponds to 3 planes: XY plane, XZ plane, YZ plane. The discussions we had about the nomenclature of the horizontal axis, like in the horizontal axis, the stresses are all normal. In the vertical axis, the stresses are all shear clockwise on the positive side, shear counterclockwise on the negative side. So that discussion remains valid, same. But what is changing here, that because of the 3-dimensional state of stress, you have to have 3 Mohr circles for each plane. XY plane, you have 1 Mohr circle. So imagine that, let's say for XY plane, let's say X belongs to 1, Y represents 2, and Z represents 3. So you have for 1-2 plane or XY plane, you have this Mohr circle. Is everybody following it? What I'm saying?
Yes.
Basically, are you pretty much you have one more circle for each axis?
Not axis, but plane. So imagine that you have 3 planes. So you have this stress element. Now you have, this is x-axis, let's say, this is y-axis, and this is z-axis. Now these are 3 axes, but we are not interested in axis. We are interested in plane. Remember, we actually talked about Mohr circle, which only talks about planar stresses, in plane, how the stresses are represented and how can we draw Mohr circle. Do you remember the discussion we had last time?
Yes.
So here you see the 3 axes corresponds to 3 planes. This is XZ plane, 1-3 plane. This is 1-2 plane, and this is 2-3 plane. Are you guys getting what I'm saying? Yeah.
Yeah. Okay. Your mouse wasn't moving when you were talking, but okay.
Okay. So, okay, just give me a second. Let me actually share. So I have to switch back between the PowerPoint slides and the document cam. Well, while we were having our discussions on Mohr circle, I told you that we are going to talk about XY plane, and I have sigma XX, I have sigma YY, then I have tau XY. And if I have, this is a representation of stresses in plane, a planar representation of stresses. Are you guys with me so far? So
Yes.
Yes.
instead of working
Yeah.
on a three-dimensional situation, I'm talking about plane. Now, plane is only XY plane. Now, I can have YZ plane, I can have XZ plane. If I have XZ plane, then instead of YY, I will have ZZ. So that you have, I mean, we have that discussion. We have been having that discussion that how the change in the axis or change in the plane will change the subscripts. So if I have XY plane, so I have sigma XX, sigma YY, tau XY. If I have XZ plane, it will be sigma XX, sigma ZZ, tau XZ. So depending on which axis you are or which plane you are, you will have these subscripts. Now, for one plane, which is let's say XY plane, or you can also have 1-2 plane. You can talk about this as 1 and 2 plane. You know that we talked about the Mohr circle representation where we have all the stresses, normal stresses in the horizontal axis. This is tau clockwise and this is tau counterclockwise. And I hope you understand by now what tau clockwise and counterclockwise means. So to draw the Mohr circle, we basically take 2 points, sigma xx and tau xy, and another point would be sigma yy and tau xy. We mark first point, assuming that tau xy with sigma xx is counterclockwise, so this is sigma xx. Tau xy, similarly, we have another point which corresponds to sigma yy, tau xy. And we got these 2 points. We actually draw a straight line connecting these 2 points. The center of this line, wherever, not the center, but yeah, center of the line which intersects x-axis will be the center of the Mohr circle. Having that as the center, you can basically draw a circle, and that represents the Mohr circle here. And when this circle intersects this horizontal axis, that becomes your principal stress. So let's say this is sigma 1 and this is sigma 2. And correspondingly, the maximum shear stress that you are getting is tau 1, 2 max. Is everybody following it so far? What I'm trying to say.
Yes.
Yeah.
Yes.
Question so far? Now, what we are doing in Mohr circle for 3D, we are doing the same thing for 1, 3 and 2, 3. So let me actually go back to the PowerPoint slide. So here you will see you have one circle for 1, 2 plane, which is XY plane, another circle for YZ plane, another circle for XZ plane. So there are 3 circles, and basically 3 circles means there is one more circle for each individual plane. This is what you are going to get when you can no longer represent the stresses in planar coordinates, when you have stresses in all 3-dimensional, because the load is very complex. The loading, complicated loading in a specific geometry causes stresses in all different directions. And then I cannot assume or approximate my stresses are only constrained or confined to a plane, a planar form. Okay. Are you guys with me?
Yes.
Yeah, we are.
Yeah.
So looking at these 3 circles, if somebody asks you, or if I ask you, if a material is ductile, at what value of shear stress the material will fail? What would be your answer? You always, we already discussed about it, that the ductile
Maximum.
fails at the maximum shear stress. So which of them is the maximum shear here?
Top.
Yeah, 1, 3.
Tau 1, 3, right? And it is this value of the shear which will be determined whether the material will fail or not. So if you think, or if you are in that state of mind that, okay, we do not need to worry about all 3-dimensional stresses, we are only concerned about XY plane. So you do all your calculations, you do your Mohr circle, you find your principal stresses sigma 1 and sigma 2, and you got your tau 1, 2, and you say, oh, my shear stress is this much, that means my material is safe up till this value. But on the contrary, what is happening that if you are not taking into consideration that all the 3-dimensional stress situation, the maximum stress is happening at tau 1, 3. So basically what you are going to do, you are basically underestimating the stresses that are coming in the in the specific geometry or specific loading scenario. Are you getting what I'm saying, guys?
Yes.
If you are not taking into consideration all the three-dimensional stresses, then you will miss this value. Unless you're talking you are talking about 1-3 plane. If you're not talking about 1-3 plane, you are either going to work up with 2-3 plane or 1-2 plane. And in both these cases, the shear stresses are less than the 1-3 plane. So it is important that you have to consider all the three-dimensional stresses when the loading is complicated, when the geometry is complicated. It is no longer a simply supported beam. It is no longer a circular shaft or circular cross section geometry with known twisting moment and so on and so forth. If it is a complicated geometry, if it is a complicated loading scenario, that means all three-dimensional stresses will come, which means you have sigma xx, sigma yy, sigma zz. All three normal stresses will come, and you will also have tau xy, tau yz, and tau xz. All three shear stresses will come. So you have to be a bit careful about how to deal with this scenario. And this specific slide tells you that you still can use the concept of Mohr circle by finding out the principal stresses, and then you can draw the Mohr circle and you can find what is the maximum shear stress, and that will define the failure of a material. Let me know if it makes sense to you guys, or if you have any questions. Okay, assuming that we all are good so far. Now we are switching gears, and now we are basically discussing about how these type of stresses. So we have so far been interested, and we have so far been involved in understanding that given a specific geometry, given a specific loading scenario, whether it is uniaxial load, whether it is bending load, or whether it is twisting load. So given a specific loading scenario, what type of stresses will appear in a material, or where those stresses are maximum? Is it normal stresses? Is it shear stresses where they are going to be maximum? Or can we find or use Mohr circle to determine those stresses? But after we obtain these stresses, the next line of argument or next thing that we need to do is, can we determine when the failure, how the failure in the material takes place? If we understand that these are the stresses that are appearing in the material, can we predict the material? Can we predict the failure of a material? What type of failure will happen, and when will it happen? So there are different types of fractures or failures. Primarily, we are classified into two components. One is called ductile fracture, which is called cup and cone fracture as well. Here you see a cup type behavior, another one is cone, and they are at 45 degrees inclination, and we tried to understand the reason that why it happens at 45 degrees in the last lecture, because the maximum shear stress happens at 45 degrees to the applied uniaxial load. So that's how you have this cup and cone fracture. And this specific characteristic of failure is called as ductile fracture. While brittle fracture is something like if you have a cast iron, or you have ceramic, or you have some plastic, where the ductility, not the plastic, where the ductility is less, or where the brittle character is very high, then you will see some sort of a cleavage plane, or basically a plane where the failure happens. It is no longer a cup and cone fracture. It is just like one specific plane, which is normal to the applied loading. So that is what we call as brittle fracture. And based on whether the material is ductile or brittle, you have different failure theories. So there are different failure theories that are there in the literature. Primarily, we deal with two theories for ductile materials, which we call as maximum shear stress theory and distortion energy theory, which is also called as von Mises theory. So we will deal with primarily these two theories for ductile materials, or for understanding the failure in ductile materials. And to understand the failure in brittle materials, we will use only one theory at this time, which is called maximum normal stress theory. So we will be basically using and trying to understand these theories and what these failure theories basically mean. So if I actually move ahead, so in ductile material, as I was mentioning, you have this cup and cone fracture, and the failure that happens in ductile material is that you have slipping of the planes. So you basically have the planes, pistil planes or slip planes, where the slipping happens and the material actually slips along these planes. And with this slipping basically means one piece of material is sliding on top of each other. So they are basically sliding, and when they are sliding, it is basically the shear stresses that are prominent. So it has been observed microscopically that in ductile materials, there is this slippage of the material systems or slippage of the crystal planes occur. And because of this slippage, it is assumed that the failure is happening because of shear, because when two surfaces are sliding against each other, then there are shear stresses being developed. So if you have high resistance to this slippage, that means material has high strength. If you have low resistance to this slippage, that means the material will just yield. It will just plastically deform very easily. So that's how the ductile materials actually fail. And I see one chat window. What is T13? Sorry.
That was the maximum from the Morse circle you had earlier.
Yeah, they were.
Okay, sorry. I am not following on some of the chat windows. Sorry for
Professor, so this figure that you're showing us right here,
that.
like what type of material would that be? So there's a pressure, like there's like a force pulling down, right? And then this is how it breaks, like it
Yeah,
kind of
force
flips.
pulling down and the upper end is fixed. So this end is fixed, it is not moving. So this end is fixed, while this end, because of the force pulling, there's an extension. So it is uniaxial load. And if you just zoom in on the material, you will see that they are all sliding, and the ductile materials basically behave like this. So all ductile materials like aluminum, steel, then copper, then plastic, then any other ductile materials that actually behave or yield or have the yield strength, they actually behave like this. They have to fail like this.
Okay.
So, and because of that type of slippage, you actually see this cup and cone fracture in these ductile materials. Okay.
Yeah.
Any other questions, guys? Okay. So moving forward, so that was the physical intuition or physical explanation of how the failure was happening. Now, mathematically, once you have got the stresses, how can engineers or designers, I mean, when you guys will work in the field, how you guys will actually get to know when the failure will take place? So this is the first theory we are learning, which is called as maximum shear stress theory or Tresca theory, or it can also be called as Guest theory. So what it says that if you have a general state of stress, that means you have all three-dimensional stress situation happening, then first what you need to do is calculate the principal stresses, sigma 1, sigma 2, sigma 3. There are formula. I'm not asking you to remember that or memorize that formula. You can always reference back, or you can draw your Morse circle and you can get the principal stresses. So once you have found the principal stresses, there will be three of them: sigma 1, sigma 2, sigma 3. Always remember that. Even if you do not have a general state of stress, even if you have uniaxial loading, then also always remember that the principal stresses are always three in number: sigma 1, sigma 2, sigma 3. So once you have got those principal stresses, arrange them in decreasing order. So basically you have sigma 1, which is the largest magnitude, then sigma 2, which has the thereafter the least, I mean, the second largest magnitude, and sigma 3 is the least of them from the magnitude point of perspective. So arrange them in this decreasing order. Once you arrange them in that order, then you calculate the maximum shear stress as the maximum sigma 1 minus the least sigma 3. I mean the least stress, least principal stress, which is sigma 3. So you take the difference and divide it by 2. That will be the maximum shear stress, and it has to be greater than equals to the yield strength divided by 2. S subscript Y is the yield strength of a material. So if you remember, the first thing that we learned about material deformation is you have got yield strength, you have got ultimate tensile strength, and this is what we are talking about, that factor, that value, yield strength. So if for any given scenario, you have the maximum shear stress is exceeding this value, SY subscript Y divided by 2, that means the material is no longer safe, it will fail. But if you have the value less than this, I mean the maximum shear stress is less than sigma, I mean SY divided by 2, that means the material will be safe. So you can determine whether the material will be safe or unsafe depending on whether the maximum shear stress is greater than half of the yield strength or less than half of the yield strength. Are you guys with me so far?
Yes.
Yeah.
Yeah.
You.
Any questions from anybody so far? If you are not following it, any part of it?
So SY is the yield strength?
SY is the yield strength, yes. Okay, so if you are understanding so far, if you're following it so far, you are with me, this specific chart is, or specific figure is what we have not yet discussed. So let me actually move to the document camera to make it more, I mean, you so what it basically says that now we are talking about two different coordinate systems. We are no longer talking about Mohr circle. What we are talking about the coordinate systems where the horizontal axis is your one principal stress sigma 1 and this is your sigma 2 and sigma 3 is okay, I'll talk about sigma 3 in a bit. So what it says that the failure envelope, so what I'm actually drawing is the envelope of failure as defined by Tresca theory. Okay, and I'll explain in a bit what I'm actually writing it here. So what it says that, let's say you have the principal stresses in the first quadrant. So this is your first quadrant. This is the second quadrant. This is the third quadrant. And this is the fourth quadrant. What it says that if you determine your sigma 1, sigma 2, and sigma 3, and they are arranged like this, you have already calculated sigma 1, sigma 2, and sigma 3, and they are arranged in this ascending order or descending order. So if the situation comes such that both sigma 1 and sigma 2 are positive, then what will happen? In which quadrant your point will lie? For example, can somebody can volunteer and let me know what that point will lie?
Would it be the first one?
This is the first quadrant, right? It is positive here, positive here. So in the first quadrant, if sigma 1, sigma 2 is positive, that means sigma 3 will be basically 0, or basically it is, we're talking about a planar stress now. We are talking about a situation where you have sigma 3 as 0. We are talking about a plane situation like this. Like this, we have calculated sigma 1 and sigma 2, and we arrange them in this order. So sigma 3, we at this point, we do not know, we know that it is 0 at this point of time. So what we are drawing this in Tresca theory, we are drawing a failure envelope. Failure envelope is given by this specific boundary. It is a hexagon shaped boundary which represents a failure envelope. So this is your failure envelope. So if you plot sigma 1 and sigma 2 and it remains within this envelope, that means the material is safe. If it is outside the plot, outside this envelope, that means the material will fail. So this specific boundary or hexagon is called as failure envelope, and it is basically the failure envelope of Tresca, or failure envelope using Tresca criteria. Is everybody following it so far, what I'm trying to say?
Yes.
Yeah?
Yeah.
So assuming that I have sigma 1 and sigma 2 both positive and sigma 1 is maximum, then what will happen that the failure envelope will be straight line. That means you either have the failure envelope like this or like this. Similarly, if sigma 1 and sigma 2 are all negative and both negative, which is in the third quadrant, and that means your point is in the third quadrant, and you know that sigma 1 magnitude wise, or basically it is greater. So in that region also you have the failure envelope given by these straight lines. But if either of sigma 1 or sigma 2 is negative, so in this case sigma 2 is negative, in this case sigma 1 is negative, so as either one of them is negative, then the failure envelope becomes one straight line, and that straight line is given by the equation, which is this. So this is the equation of a straight line when you have sigma 2 is negative. I mean, here sigma 2 is negative and here sigma 1 is negative. Are you guys following what I'm trying to say?
Yes.
Maybe it is hard to completely get at this point of time, but let me try to explain it again. So this is the horizontal axis where we are plotting sigma 1, principal stresses, the first principal stresses. We know that in a planar coordinate system, we have got sigma 1 and sigma 2 and sigma 3. The third principal stress would be 0 for planar situation. For planar situation, all the stresses outside the plane is 0. So sigma 3 is 0 here as well for planar situation. So in that case, if I arrange the sigma 1 and sigma 2 like this, and somehow I found that my point sigma 1, sigma 2 comes at this, which is point A. So is the material safe or unsafe? Let me ask this.
Should be safe at point A.
Safe because I told you so, right? I told you because this is the failure envelope. Any point line within this envelope is safe. And this is the origin. If I join a straight line using from the origin to this point A and extend it, that we call as load line. Load line basically means that, let me take one example. So let me take an example of a uniaxial. I apply load P and somehow I got the stresses calculated, the principal stresses I calculated as load divided by cross section area. Because for uniaxial load, the principal stresses will be in the same direction. So sigma 1 comes out to be P divided by area, and that comes out to be this point A. Okay. Now, the next question is that is the material safe or unsafe? You already told me it's safe because it is within the envelope. So that's good. That basically means the material is safe. Now, the next question is, what is a factor of safety? How much load I can increase such that I will still remain safe? So to do that, what we do, we actually extend this line, joining the origin to this point A, and keep on increasing this line and see where it intersects the envelope. So I found that it intersects the envelope at point B. So this is the point at till that value, I can increase the load or decrease my area such that my stresses will keep on changing. Principal stresses will keep on increasing. But I can only increase up to this point, because after that, the failure will take place. The material will fail, and it will fail in basically having a cup cone fracture because it is a ductile material. So we are talking about ductile material, so it will fail. But before failure, you can increase the load or decrease the cross section till this point, which is this intersection point along this line. Are you with me or understanding what I'm trying to say?
Just to clarify, if it lands on the line of the envelope, it's still safe?
It's still safe, yeah.
Okay, thank you.
So this equality here basically means you can still land on the line.
Okay.
Yeah. So if you land on this line, you are safe. The moment you go to this point, you exceed this boundary, you are basically means the failure will take place. And this is what we call as load line. Load line basically means if you keep on increasing the load by the same amount, by the same proportion, that you are not changing the slope of this line, you are increasing the same magnitude. So keep on increasing the load or decrease the cross-section area such that the ratio of P over A remains, I mean, it increases by the same proportion. So that's what I mean when I say increase in the same proportion. It is the same loading line. Now, if somehow the material changes or the calculation of stresses changes and the stress comes out to be here at point C, is it safe or unsafe?
Safe.
Safe, right? Now, if I have to calculate the factor of safety, I will draw another load line, which will be joining this, and it will intersect this envelope at point D. So then wherever it intersects, that becomes another load line, second load line. And we have to see where it is actually intersecting the failure envelope. Wherever it is intersecting, that will define the maximum limit, maximum load I can increase, or maximum increase in the stress that can take place. So the factor of safety will be what? It will be calculated as this length OB divided by OA. That will be your factor of safety. It basically means that you can increase the load by this factor, because till I move to point B, I am safe. So if I measure this length and I measure this length and take the ratio of that, that will give me the factor of safety. Are you guys getting what I'm trying to say?
Yes.
Yeah.
Everybody following what I'm trying to say here?
Yeah.
Yeah.
So, Professor, that other line, what does that represent? The CD
This
line?
one?
Yeah.
This one is a different load line. It basically means the load has changed, or the area has changed such that now point does not lie in this line. It actually changes its magnitude, or principal stresses are a bit different now.
So the new load line would be like at D?
Yes, will be at D. So for this load line, the factor of safety will be from OD divided by OC.
Okay.
So what you have to basically see is always find out what your sigma 1 and sigma 2 is, and then plot that in this coordinate system where horizontal axis is sigma 1 and vertical axis is sigma 2. And then you will actually put, let's say the point comes out to be here. Now in that case, again, the load line will be joining from origin to this point, and then wherever it actually intersects, that basically becomes your new, defines your new factor of safety.
Okay.
Okay, so that is what the load line basically means. Load line means that the stresses can be increased by in the same proportion, or basically the stresses. Okay, what I'm saying here is that sigma 1 and sigma 2 are getting increased in the same proportion. The slope remains constant. So this is sigma 1, this is sigma 2. If you keep on increasing the same line, sigma 1 and sigma 2 ratio remains constant. The ratio of sigma 1 and sigma 2 remains constant. That is your load line. This load line, the ratio of sigma 1 divided by sigma 2, or sigma 2 divided by sigma 1, whatever it is, y over x, slope y over x, delta y over delta x. So if it remains constant, that is what you call as proportional loading. That defines one load line. Is it making sense, guys?
Yes.
Yeah.
Any questions so far? Okay, if not, then I will move back to the slide format. So this is what it is showing, that you have case one. Case one basically means your sigma 3 is 0. In this case, both sigma 1 and sigma 2 are positive. In that case, the envelope will be a straight line like a square. But if you are in this quadrant where your sigma 1 of the principal stresses is negative, then you have the straight line basically following. The failure envelope will be a triangle, and in the square here and triangle here. So, and in totality, it will be just like a hexagon. So this is what the failure envelope of a Tresca theory. The shaded region that you are seeing is non-yield region. Non-yield region means it is the material is not yielding. It is safe. It is basically elastic. The moment you actually exceed the failure envelope, the yielding will take place. Yielding means the material will start yielding or start plastically deforming, and that means the failure is taking place in the material. Okay. So here it is the same thing that we have been doing. I was just showing how to calculate the factor of safety. So if you keep on increasing the load line basically means the ratio of sigma B and sigma A remains constant. It is the slope remains constant. So if you keep on increasing the load in the same proportion such that the ratio of the stresses, the principal stresses remain constant, then the factor of safety can be calculated by the length of this line where it intersects the envelope divided by the actual current coordinate. So if your current coordinate is at point A, so this is the length OA, which will be in the denominator, OB will be in the numerator, and you can calculate the factor of safety by that. So that's basically is about the Tresca theory. Any questions so far on this? Okay, if not, then we move back, or we move not back, we move ahead with a new theory, which we call as von Mises theory. Now, von Mises theory basically means that you take into account all three stresses again, principal stresses again, but you calculate the specific formulation which we call as von Mises stress. So if you look at this specific equation where it is sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square divided by 2, and then you take the square root, this specific expression is called as von Mises stress. You remember that when we were doing SolidWorks simulation, it was always listing us von Mises stresses. So if you remember from those simulations, the simulations always talk about von Mises stresses, and it was also giving you a yield value of the yield strength. So the von Mises stress criteria says that if this expression, which we call as von Mises stress, which is a combination of principal stresses in a certain manner, if this expression or this stress is greater than the yield strength, then the failure will take place. So that is what is von Mises criteria is. In Tresca theory, we were using only maximum shear stress theory, maximum shear stress criteria. But here we are talking about a von Mises stress criteria. Now, if I look at this equation from a mathematical point of view, if some if a student from a maths class actually look at this equation, forgetting about what sigma 1, sigma 2, sigma 3 means, what sy means, if you look from the mathematical perspective, this equation represents the equation of an ellipse. That's what we actually see here. So this is basically the equation of an ellipse, and that will be the failure envelope for the von Mises criteria. And you will see that it is encompassing the failure envelope of the Tresca criteria we have just seen a while ago. So Tresca criteria is enclosed inside the envelope of the von Mises criteria. Is it making sense, guys, so far?
Yeah.
So let me actually ask random student from the list here. Trevor, Norman?
Yeah.
Yeah, so can you help us to understand that which of the two criteria, there are two failure theories we have learned so far, Tresca theory and von Mises theory, right? You agree with me?
Can you say the second one again?
The von Mises theory. This is the von Mises theory we have learned.
Oh, okay, yeah.
So we have learned the two types of theory, Tresca theory, which gives me envelope like this, hexagon, and a von Mises theory, which gives me envelope like this, which is like a ellipse. You agree with me?
Yeah.
Great. So if somebody asks you that as a designer, which one of the two theories would you prefer? Or why, out of these two theories, which one would be your favorite theory to use? Or which one will be the go-to theory for your failure analysis? Which will you pick?
Von Mises.
And why?
It covers, I'm assuming it covers a bigger area.
That's a good point. It covers a bigger area, sure. So as a designer, the objective, it depends on the objectives. Let me state that way. So if as a designer, your objective is weight saving, then you will go for von Mises theory because it is having a bigger envelope, bigger failure envelope, or bigger area under the failure envelope. But if you are conservative, if you want to be conservative, or if you do not know much about the loading scenario and you want to have a high factor of safety, then you would like to go with Tresca theory, because in that scenario, you are within the failure envelope of the von Mises criteria. Are you guys getting what I'm trying to say here?
Yeah.
Yeah.
If you are a conservative designer, go with Tresca theory. If you are a very aggressive designer where you weight saving is the primary goal and you can take risk in the failure, well, not like you are assuming that failure will take place, but you can take risk, then, or you have that flexibility to take risk, then you can go with von Mises criteria, because this will give you less conservative design. Okay. Let me know if you guys are following what I'm trying to say and why I'm saying that.
Yeah, that makes sense.
Yeah, makes sense.
Mm-hmm. Any questions so far?
You said this one is for when you can take risks?
When you are
The larger one.
if you want to be conservative, go with Tresca, because then you are dealing with less failure, less area under the failure envelope.
Okay, thanks.
Yeah, but if you are not a conservative designer, you can basically go forward with von Mises criteria. So let me explain what is happening here. So if you see this line represents a load line. Now it is characteristically called pure shear load line because sigma 1 and sigma 2 are increasing in the same proportion in 45-degree line. So this is a load line where the stresses are all shear stresses. Shear stresses will cause equal amount of sigma 1 and sigma 2. So if you are applying twisting load, twisting, everybody understands by now that twisting or the torque results in shear stresses. So if you apply twisting load and you keep on increasing the twisting load magnitude, the stresses will actually follow this load line. Now you see this load line and you see that it first intersects a Tresca theory envelope. So as a designer, you will say that I don't want to exceed this limit because I would consider this as a failure. So as a conservative designer, you can basically set your criteria of failure at this point. But if you are not a conservative designer, you say, okay, I can take some more risk rather than saying that I can have a failure at this point. I will assume that my failure will take place a bit more. I can increase a twisting load a bit more. I can have a more, I can say that I can have more estimate or more, how do you say that? More allowable for increasing the load. Then you will basically go with the von Mises criteria and you increase the load limit. And while doing so, you are basically increasing the capacity of the design or you're certifying that a design can withstand more load. So that is what a less aggressive or less conservative designer would be. Does it make sense what I'm trying to say here?
Yes.
Yeah.
Yes.
Any questions or anything that you're not following? If I can explain again.
What does DE and MSS mean?
Okay, DE is the distortion energy theory, which is here, DE, distortion energy. And MSS is basically maximum shear stress. That is called Tresca theory that we have learned so far. So I just showed you, just going back the previous slide. You see here, this is Tresca theory can also be called as maximum shear stress theory, or it can be called as Guess theory. So MSS represents maximum shear stress and DE represents distortion energy, which is nothing. Okay. So this shows, or this basically further put some numbers here, which says that if you talk about Tresca theory, the yield strength, the shear yield strength, S subscript SY basically means shear yield strength. So shear yield strength for Tresca is 0.5 times of the actual yield strength of the material. But for von Mises, the shear yield strength will be 0.577 times the yield strength. So basically it means you are more conservative with Tresca, but with von Mises, you are less conservative. That's what it basically means. Are you guys with me so far?
Yes.
Yeah.
Okay, and these are just not just somebody has come up with those theories. There is a specific empirical data or experimental data that actually falls on this failure envelope. So this is basically the data points that you are seeing, the black and white dots represents the data points, represent the failure of a material for different system. So if you have nickel, chromium, molybdenum, steel alloy, the white circles or the unfilled circles represent the failure of the material. If you have AISI 1023 grade steel, you have small black dots, then you have unfilled squares represents 2024 aluminum, and similarly you have 3SH aluminum. This is different alloys of the aluminum. So for different types of ductile materials, the failure data points are, you can see, are all lying in this within the envelope of the von Mises criteria. So it remains either at the boundary or very, very close to the boundary. So the failure data points were experimentally observed to actually follow this specific curve, which is called von Mises envelope, failure envelope. So actual failure is happening at this boundary, but as a designer, you are limiting your design only to this Tresca theory. That means you're a conservative designer. But if you want to take some more risk and go to the von Mises envelope, then it matches the actual failure data points, but at the same time, you are seeing the data points can exceed as well, or data points can lie within as well. So there can be failure within the safe zone. So there is a scatter in the data point. So basically it is a risky decision to take that you want to consider this as a safe boundary. So that is why as a conservative designer, you can basically go with Tresca theory. Any questions, guys, so far?
Can you say again what the different shear yield strengths were, the 0.5 and the 0.577?
So it basically says that 0.5 times the yield strength is basically the point at which the failure will take place. Let me actually go back to the Tresca theory. So if you see here, the failure theory or envelope is given by the maximum shear stress, which is half of the maximum principal stress minus minimum principal stress. And this has to be greater than equals to this number, which is half of the yield strength. Remember this, what we are actually using this equation.
Yeah.
So this is your shear stress, which is basically the maximum shear stress for calculation, and this has to be greater than equals to half of the yield strength. So basically we call this number 0.5 times SY as the shear yield strength, SSY.
Okay.
And for von Mises stress, because of the calculations, this is basically going to be, if all other sigma 2 is 0, sigma 3 is 0, you found that this is going to take place at 0.577. That is what we call as shear yield strength for.
Okay, I get it.
Any other questions, guys? Okay, so the last one, failure theory we are basically doing is for brittle materials. For brittle materials, there are different theories, but the most common theory is the maximum normal stress theory. What it says that you calculate the principal stresses, arrange them in this order, take the maximum, which is sigma 1, and if sigma 1 is greater than the ultimate tensile strength of the material, the failure will take place. Or you take the minimum of them and compare with the compressive strength of the material, the ultimate compressive strength of the material. And if the sigma 3 is less than that, that means the failure will take place. And the envelope will be just a square. It's basically just one square that you are actually seeing here. So any material that actually, or any data point that comes within this square, it means safe. Any data point that goes outside the envelope is unsafe, is where the failure will take place. Make sense?
Yes.
Professor, I don't know if this is a dumb question, but why is the non-failure like square? Why is it like off-centered?
Okay, that's a very good question. Actually, it is not a dumb question. The reason is that most of the times, especially for brittle materials, the tensile strength and compressive ultimate strength are not the same. So if you see this magnitude SUT, ultimate tensile strength here, and this is ultimate tensile strength positive, this is ultimate compressive strength negative, this is ultimate compressive strength negative. These and these are same, these are different. So it may be like 100 megapascals and this will be negative 300 megapascals. So it fails in under compression load. It can withstand more load, more capacity to withstand loading, compressive loading. So the load is basically ultimate compressive load is higher than the ultimate tensile load in magnitude.
Okay, so pretty much this square is gonna change depending on the material, right? It's not like
Yes.
general.
Yes,
Okay.
yes. So because these are variables, so depending on the material, you have different variables. I mean, SUT will be different. Let me go back. That is actually a good question as well. Let me go back to this slide. So here you see for different material data points, everybody is lying on this envelope. So how is it possible? They have different, each one of them have different values. So what you are seeing in this axis, that is normalized. So it is sigma 1 divided by SC, which is the compressive strength. Sigma 2 divided by SC, which is the compressive strength. It should be not compressed, it should be shear stress. Shear yield strength. So it is basically getting normalized. So it is values are ranging from 0 to 1, no matter what material you are choosing. So that is why you see all the data points are lying on one envelope. So if you are not normalizing the magnitude of this axis, then your envelope will keep on changing depending on the different material, because different material will have different strength. Okay, so SC is represent here actually SY, yield strength. That's what I was referring to. So different material will have different yield strength. So the envelope will be increasing or decreasing in its area. But if you normalize the axis such that it scales from 0 to 1 and 0 to 1, then means all the material data points can be described by one figure itself. Are you guys getting what I'm trying to say?
Yeah.
Yeah.
So that's the good questions actually. Any other questions, guys, so far?
I have a question.
Go ahead.
The sigma A and sigma B, is that coming from the Moore circle?
Yeah, it is coming from the Moore circle, or there are equations that you can use to calculate those principles.
Okay.
Any other questions, guys? Okay, if not, then I will take a couple of minutes break, like 3-4 minutes break, and we will come back to do this specific example in SolidWorks simulation. So I have already uploaded the SolidWorks files. Please open the SolidWorks software and see the static simulation results that are there, and we will discuss this specific case study. So let me actually take a very short break, and okay, guys, are you able to open the SolidWorks files or components in the software?
Yeah.
Okay, so let me actually do the same thing here. Okay, so if you have uploaded that, so what I did, I just created specific components here. So you have this rod, and this is a specific another rod which gets assembled. So there are two parts that are, and I did the static simulation. It is just like a wrench, or you are designing, let's say, or you want to design. So you have one end is fixed, and you are applying load from this end. And if that is a scenario, what is going to happen? So basically, I have defined the material properties for these two parts. So this is the first part, and this is the other part, the rods, plain simple rod. And the components, the connections have been defined here. Fixtures, it is basically fixed at this specific location, and then I applied a load of 100 Newton from this end. So if that is the situation, and I created the mesh and run the simulation, you will basically see the stresses. Now here there are 3 plots. Now I can edit. By the way, are you able to see this screen, the SolidWorks screen that I am showing?
Yes, we can see it.
Okay, great. So I just thought I am not sharing it. I'm just saying things which doesn't make sense to you guys. So, okay, the first thing that you will actually see that if you run the simulation, you will basically end up with these type of stresses. The von Mises stress, which I just explained to you how it is calculated. So it is basically given by these magnitudes, and this is the representation of the von Mises stress here. And this SolidWorks also tells about the yield strength. So we have just learned that if my von Mises stress, the maximum value of the von Mises stress in magnitude is greater than the yield strength, then the failure will take place. Now for this specific loading scenario, for this geometry, I am seeing that the maximum von Mises stress is less than the yield strength. That means failure will not take place. I still have some margins or increasing the load or decreasing the diameter or cross section or reducing the cross section such that I can increase the value of the von Mises stress such that it can reach up to the yield strength. Or I can just say that if I divide this value of von Mises stress with this yield strength, I will get a factor of safety. I mean, reciprocal of that, yield strength divided by the von Mises stress. I will get a factor of safety. Is everybody with me so far?
Yeah.
Yeah. And
Yep.
you actually look at that the von Mises stress is maximum at this point and also at this, because this is the contact area, and also the stresses are a bit maximum at this location. So if I have to ask you, what is, if you have not seen this contour plot or stress plot, what would be the critical locations in the specific design where the failure will take place?
Good point.
Sorry? So for sure here, it is very trivial question to ask that wherever you basically have the maximum von Mises stress, those are the critical locations. You have maximum von Mises stress at this region, and you have maximum von Mises stress at this region. So basically you are going to have the failure happening, takes place at these specific locations in the material or in this specific design. Now, if I just try to show you the animation of the displacement, because that's what is important always. So if you see, the displacements are basically happening such that you're applying the load, this is getting bended, and because of this bending, the loads are getting shifted to this wrench as well, or this rod as well. And this rod is being subjected to both the bending as well as twisting. So we will see today what we are going to do with this specific simulation exercise is to make sure we understand or we have some handle or we have on the stresses. Can we calculate these stresses, the von Mises stress or the principal stresses? So can we calculate the stresses based on the geometry of the figure and based on the load, and whether that matches with the simulation values. So instead of just going with the von Mises stress, what we are going to do is we are going to first find the normal stresses. But before I actually describe you in detail about the stress calculation, let me actually go back to the document camera and just let's discuss about what the dimensions are and what the geometry looks like. So basically what we have here we basically have a system where you have this rod, and let me actually give you the dimensions. So I'm not making the actual representation, but it is an L-shaped rod which has got load of what it is 100 newtons. And let me actually give you the dimensions. This diameter of this rod is 20 millimeters. Diameter of this rod has got two sections, one bigger diameter and one smaller diameter. So the smaller diameter was 25 millimeters. The bigger one has a cross section of 38 millimeters. I mean, you can measure this using the model itself. Since I created this model using these values, I'm just writing these values here. So this is 25 millimeters, and the length from this portion to this portion is 330 millimeters. So I did everything in millimeters. The dimension that you are seeing in the slide, PowerPoint slide, is in inches. I just converted into millimeters for making sure that all the dimensions are consistent. Okay, and this length is 300 millimeters. Actually, I've used 275 millimeters based on my assembly. Okay, so what I was basically concerned with, that if I have to calculate the stresses in the material, how can I calculate that? So first, you know that you can make a free body diagram by replacing this load at this end by a bending load and a twisting moment. So it can be replaced. So this end is fixed. So it can be replaced with P is equals to 100 newtons, and along with a twisting moment T given by 100 newtons times 275 millimeters. Is everybody so far agreeing what I'm trying to say here?
Yep.
Yeah.
Yeah.
Yeah. So given that, can you find the stresses at this location, which is distance 355 millimeters away from the point of application? How to calculate that? So if I have to calculate the stresses, what I know that I have two types of stresses: sigma bending, and that will come in the direction of the axis. So the direction of that is basically x. So the coordinate system in SolidWorks simulation is x, y at the top, and z like this. So sigma bending, which will be calculated as m y divided by I. For circular cross section, it will be p times 355 millimeters. Y will be d divided by 2. I is pi d4 by 64. So it basically comes to 32 times p times 355 by pi d cube Newton per millimeter square. That will be your bending stress. Can somebody calculate this number, please? Where d is your diameter, which will be 25 millimeters. So 32 times 100 newtons times 355 millimeters divided by pi 25 cube Newton per millimeter square. That will be a bending stress. Can somebody tell me what the number looks like for this?
I got 23.14.
Okay, 23.14 Newton per millimeter square.
I got
So
the same.
with the bending stress, and what would be the direction of this bending stress, guys? Or rather than, let's go back to the software SolidWorks simulation and tell me what stress I should be looking at. So if I go back to my SolidWorks simulation, excuse me, and I am in this stress plot. Now, what should be the, if I do the edit definition, I definitely know that this value that I'm getting is much, much higher than what I calculated. So definitely the value that I have calculated just now, the bending stress, is definitely not equal to the von Mises stress. So if I look at the display, I see there are so many stress components: sigma x, sigma y, sigma z, tau xy, tau xz, tau yz, P1 first principal stress, second principal stress, third principal stress, one misses stress. Excuse me, stress intensity is P1 minus P3, triaxial stress, so on and so forth. Which of these values do you think will be giving me the bending stress? Do you guys see what I'm trying to ask here? Can anybody volunteer and let me know or tell me what the bending stress will be in which direction?
Is it in the y direction?
Y direction is basically up, and when bending happens, how the bending happens on this rod, this basically deforms like cantilever beam, right? So if when it deforms like cantilever beam, what should be the direction of the stresses?
I think the one that sticks out, that would be in the Z, no?
Okay. Let me actually try to show you the animation of that displacement plot again. So when you look at this, now if you not look at this specific, but you look at this, what is happening to this rod? It is basically bending, right? It is deforming like this. So when it is deforming like this, what do you think where the stresses would direction would be? Is it in the X direction, it will Y direction or Z direction?
Would it be X because it's kind of getting elongated?
Yeah, it is elongated in the X direction or getting shortened in the X direction. So the stresses would be happening in the X direction primarily. So if I actually see and go to the edit definition and select sigma X, what value are you getting? .569 E7 Newton per meter square. And how much you are calculating? What is the value calculated? 23.14, right? And that is equal to 14 E7. That is very, very close. And if you look at that, you see the top part is in tension. The bottom part is under compression, the same magnitude, almost similar magnitude. Negative 2.541 E7 at the bottom, because bottom part is in compression in the X direction. Remember, it is in the X direction. It is the X direction on which the shortening and compression happens. So in the X direction, the compression happens. In the X direction, the tension happens. So in the positive side, you have 2.569 E7, and what we calculated is 2.314, which is pretty much close. I mean, there will be some difference because we are not using three-dimensional stress situation. This finite element models use three-dimensional stress situation. We are only using simple bending formula we learned from 373 class. And still we see that we are in the same ballpark range of what the simulation values give us. Are you guys following, everybody in the class?
Yeah.
Yeah.
Yeah. If you take any other stress value, whether it is sigma y, sigma z, tau xy, you will never be able to match this value that will come in the bending. And this is what we actually know from bending. The top will be in tension, the bottom will be in compression. If you take sigma y, let's say, it is it is an order of magnitude less. You see, it is 9.37 E6. And we have 2.3 E7. We have one order of magnitude less value. So it is no longer in tension and compression sort of thing. I mean, there are some pockets, but it is not a bending stress. It is actually some context stresses that are actually happening. Are you guys getting what I'm trying to say here?
Yeah.
So that is a reason that I was basically emphasizing on the subscripts, that you guys must understand the subscript. Otherwise, if somebody asks you to do the simulation, you can do all the simulation. But if somebody asks you to interpret the results, it becomes difficult to interpret if you do not understand that this sigma due to bending is in the x direction, sigma x, not sigma y or sigma z. So that is what you guys basically need to focus on, that what should be the subscript of the stresses based on the applied load. So far you actually know how to calculate them. But what we need to do is we have to basically make sense of the results from the simulations. And you cannot make sense of the results unless you know that this is sigma x. It is positive on the top, negative on the bottom, but it is sigma x in the x direction, because stretching and compression is happening in the x direction. Okay, now let's say I go back to the document camera. So I just calculated bending stress because of this load. Now this is still remaining, the twisting moment. Can anybody tell me what the twisting moment causes, what type of stresses it will cause at this point?
Shear stress?
Shear stress. And how to calculate that? We know that shear stress to torsion is given by T times R divided by J. J is the polar moment of inertia. Now tau is going to be 100 newtons times 275 millimeters. I know this number 275 millimeters because I assembled the parts that way. You can measure it in the model itself. You will find this number. Otherwise, if it is different number, you will let me know what that number is. Anyways, if I use this formula, Newton millimeters, R is D over 2, J is pi D4 divided by 32. Polar moment of inertia for circular cross section is given by this formula. I'm not expecting you to remember this, but you, at least for circular cross section, it is quite useful if you remember that polar moment, actual area moment of inertia is pi d4 by 64, and for polar moment of inertia, it's pi d4 by 32. So if I simplify, it comes out to be 16 times 100 times 275, 16t divided by pi d cube. Now d is again 25 millimeters. Can somebody tell me what that number will look like? What we are calculating is shear stress, tau, tau, and tau.
$17.50.
How much you get? 17.50. Is everybody getting the same number?
I got something else. Is that is the diameter still
25.
Now it's 20? Oh, okay, that's why.
It's 25. We are calculating on this specific section.
My bad, that was my mistake. Yeah.
So what is that value? This is
It should be 8.96.
8.96 Newton per millimeter square. Okay. Now let's go back to the simulation and see what value we are getting there. But before you actually go back to the simulation, you have to tell me what is it. Is it tau xy, tau yz, and tau xz? Without that, you cannot match. You cannot basically predict what is going to happen. If I go back to this, is it visible to all?
Yeah, we can see SolidWorks.
Yeah. So now if I have to pick a specific tau, tau basically shear. Now shear of three types: xy, xz, yz. Now what do you think? Which of these two or three values it should be?
YZ.
Okay. So that is the mistake you will make because it should be tau xy and xz, not yz. And you can easily verify that if you select tau xy would be coming on the top face and the bottom face. So no, not the bottom, the side face, this left face and the right face. So if I just press yes, you will see that the value is very high. It is not exactly the value we have calculated. And the reason being, am I making any mistake here? Give me a second. The values that you are actually seeing is 1.4 and what you calculate is 8.96. So that is still not exact value. XZ. Okay, here is it. Okay, no, that was making sense as well. I will explain in a bit what was the problem. So tau xz is basically in the top and in the bottom. And the top we have 1.07, which is basically 10 Newton per millimeter square. What you calculate is 8.96, which is 9 Newtons per millimeter square on the top and on the bottom. Now, because of twisting load, you have the same coming on the side, but because of the extra bending, the sideways twist side, the shear stresses at the sides, which will be the tau x y direction, would be bit more than this 1.07 or 10 Newtons per millimeter square. I don't know if you are following with me or not.
I think I am. It's because you also have the
Yes.
deflection, correct?
Yeah, you don't have a bending load. So let me actually quickly wrap up our discussion for this evening by going back. So this is the twist. This is the shear stress happening due to twisting, due to twisting moment. Now there is shear due to bending as well because of this bending load. Now we know that the bending shear stress due to bending follows like this basically. So this is your x, and so it is 0 at the top, 0 at the bottom. So that means at the very top, you only have this shear due to twisting. But at the side, so if I have a side like this, I'm not sure if I am making sense with this schematic. So this is your x, this is your y, this is your z, and at this point and at this point, it will be shear due to torsion only, nothing else. That is why this value in simulation, it was 10 Newtons per millimeter square. Our calculation was 8.96, which was 9 Newton per millimeter square at the top and the bottom. But at the side, at this side and this side, and this at the top and bottom, it will be tau this direction, and this direction, it will be tau x z, and at the bottom as well tau xz. And a sideways, it will be tau xy. But apart from torsion, this bending shear stress due to bending will also appear, and that will cause it to increase its magnitude. I don't know if you are following it with me or not. I will try to explain this specific example and specific scenario in the next lecture, because I think we are overshooting our time at this point of time. So we will come back to discuss this, but the overall reason I was trying to make sure that you understand this specific subscript, because without understanding that which of the shear stress, whether it is xz, yz, or xy, the values will not make sense to you. If you look at tau yz, it will not make sense to you. If I actually go and say plot tau yz, or sorry, tau xy. So if I plot tau xy, the values will not make sense to you, because what you calculated is only 10 or 9 Newtons per millimeter square, but it is showing 40 Newtons per millimeter square. That means something is wrong. And if you do not know why it is coming out to 40 Newton millimeter per square, you will be just scratching your head and just don't understand why is it happening. And now we know that basically the reason is that this is due to the bending plus twisting. And that is why it is more than the 10 Newtons per millimeter square that is coming in the top and bottom. Okay, I don't know if it still makes sense, but we will actually resume our discussion from this point onwards in the next lecture. Okay, any questions before we wrap up our today's session?
No questions.
Guys, if there are no more questions, then let's wrap up our discussion today, and I will see some of you guys on the Wednesday lab.